Picture this. We're building a spaceship. Not some Hollywood fantasy with impossible engines and made-up physics. This is real hardware, the kind engineers could actually assemble within the next few decades using principles we already understand. That limits our ambitions in some ways, sure. We won't be hopping between distant stars or bending space-time. But it opens up something equally thrilling. Every major world orbiting our own sun becomes a potential destination. Think of it as the ultimate travel itinerary, except your stops are planets. So here's the question that matters. How much time would we actually need to visit each one? The answer turns out to be far trickier than simply measuring distances on a chart. Space navigation isn't like plotting a road trip where you pick 2 points and draw a line. Everything here operates under rules that feel counterintuitive at first. The core challenge stems from the fact that nothing in our solar neighborhood ever sits still. Every object, from tiny asteroids to massive gas giants, follows its own oval path around the sun. Our home world tears through space at roughly 107,000 kilometers every hour. Meanwhile, every other planet races along its own track at its own unique pace. When you aim a spacecraft toward Jupiter, you're not targeting where Jupiter is right now. You're aiming at where Jupiter will be months from now, when your ship finally arrives there. Imagine trying to hit a bullseye on a spinning wheel while you're also spinning on a different wheel. Now add the constraint that you get exactly one attempt. Miss that target, and you've just incinerated years of preparation plus hundreds of millions in funding. The stakes are that high because space travel operates on the thinnest possible margins. There's no room for improvisation once you've committed to a trajectory. The culprit behind this unforgiving reality is fuel, or more precisely, the lack of it. Your spacecraft carries only enough propellant to execute a very specific sequence of maneuvers, calculated down to the second. Think about driving cross-country with just enough gasoline to reach your destination if you follow the most efficient route perfectly. One wrong exit, one stretch of excessive speed, even braking too hard a few times, and you're stranded. That's the constant pressure mission planners face. Every burn of the engines must serve a purpose. Every course adjustment must be justified. It's a ballet of precision where even small deviations compound into mission-ending disasters. To succeed, we need to stop fighting the fundamental forces and start using them. Gravity, the most dominant force across cosmic distances, can either crush our plans or become our greatest tool. The trick is learning when to resist it and when to let it carry us. But before we can harness gravity's power, we first have to break free from its grip here at home. Escaping Earth's gravitational well represents the most energy-hungry phase of any planetary mission. The sheer amount of fuel needed is staggering by any measure. During the initial 2-minute burn, our rocket guzzles enough propellant to fill an Olympic swimming pool every single second. All that violence and fire serves one purpose: lifting us beyond the atmosphere and crossing into the black. Once we're up there, we're traveling at over 20,000 kilometers per hour, faster than Earth's surface. At that velocity, we can outrace the planet's gravitational pull and settle into a stable, circular path around it. Now comes the part where orbital mechanics starts defying everyday intuition. From inside our spacecraft, it feels like we're flying in a straight line. The ship doesn't turn or bank like an airplane navigating a track. Instead, Earth's gravity warps the fabric of space itself, bending our supposedly straight path into a curve. The more speed we add, the gentler that curve becomes. Push hard enough with the engines, burn enough fuel, and we straighten our trajectory until we're traveling farther and farther from Earth. Conversely, if we slow down from our current orbit, gravity tightens its grip. The curve grows sharper, and if we decelerate too much, that curve points straight down toward the surface. That's not where we want to go. So we do the opposite. We double our velocity to over 40,000 kilometers per hour relative to Earth. That acceleration breaks the planet's hold on us completely. We're finally free to venture outward into interplanetary space. Our total speed relative to the Sun now sits around 150,000 kilometers per hour. We've become just another object hurtling through the solar system, subject to its rules. But those rules come with constraints we can't ignore. Just like every planet, moon, rock, and ice chunk out here, we're now caught in the Sun's gravitational field. It's the same principle as orbiting Earth, just scaled up enormously. Because most of the solar system exists on a relatively flat plane, we essentially have two choices for direction. We can head inward toward the Sun, or we can head outward away from it. Either way, our path will curve around the Sun's massive gravity well. Remember, straight lines don't exist in orbital mechanics. We control our trajectory by adjusting our speed. Accelerate to climb outward, decelerate to fall inward. On the surface, that sounds manageable enough. If our goal were simply wandering aimlessly through space, this would almost be easy. But we're not wandering. We're aiming for specific targets. Reaching a particular planet and then slowing down enough to orbit it requires calculations of extraordinary precision. The slightest error early in the journey compounds into a massive miss later. There's no GPS out here, no ground control constantly correcting our course. We're largely on our own once the main engine shuts down. So the best way to understand how all this works is to actually attempt it. Let's pick our first destination and work through the challenges step by step. The obvious choice might seem like the closest planet, but that's not where we're headed first. Instead, we're going to tackle the hardest destination in the entire solar system: Mercury. You might assume Mercury would be simple because it's relatively nearby, only about 80 million kilometers from Earth. But proximity doesn't equal accessibility when you're navigating gravity wells. Mercury orbits deep inside the Sun's gravitational field at an average distance of just 58 million kilometers. To avoid getting pulled into the Sun, Mercury has to move incredibly fast, racing along at 170,000 kilometers per hour. That speed creates our problem. From our current position, we need to slow down dramatically to begin falling sunward. Then we need to control that fall precisely so we don't overshoot Mercury or crash into the Sun. It's the hardest planetary rendezvous we'll attempt, which makes it the perfect first mission. Master Mercury and everything else becomes easier by comparison. Starting from our position just beyond Earth's gravitational influence, we face two major obstacles that define this entire mission. First, we must shed enough velocity to begin our descent into the Sun's gravity well without overshooting our target. Second, we need to control that inward fall so precisely that we arrive at Mercury's orbit moving slowly enough to stay. Right now, we're traveling at roughly 150,000 kilometers per hour relative to the Sun's reference frame. To initiate our sunward plunge, we have to reduce that speed by nearly half through a prolonged engine burn. We're essentially reversing all the work we did to escape Earth, surrendering the momentum we fought so hard to gain. This deceleration allows the Sun's gravity to curve our path downward until it intersects with Mercury's orbital track. That part sounds straightforward enough, almost simple compared to what we've already accomplished, breaking free from Earth's pull. But completing this maneuver successfully only sets us up for an even more daunting challenge waiting at the end. Falling toward the Sun operates like rolling down a steep hill, where gravity accelerates you faster with every passing moment. The closer you get to the Sun, the harder its immense gravitational field pulls on your spacecraft, accelerating you further. We start our descent moving relatively slowly, but by the time we reach Mercury's orbital distance, we're screaming along. Our velocity will climb to around 210,000 kilometers per hour as we approach the innermost planet's neighborhood. Here's where the real problem emerges. At that speed, we're moving far too fast for Mercury's weak gravity to capture us. If we don't find a way to bleed off that excess velocity, we'll rocket past Mercury and keep falling deeper. This exact scenario played out with NASA's Mariner 10 probe, launched back in the early 1970s using similar physics. That mission reached Mercury in just 5 months by falling straight down the Sun's gravity well with minimal course corrections. The downside was that Mariner 10 arrived moving so fast that even its most powerful engine burn couldn't slow it enough. The probe had no choice but to gather whatever data it could while screaming past Mercury at breakneck speed. In theory, we could fire our main engines again for an extended burn to scrub off all that excess velocity. But doing so would require carrying far more fuel than any realistic spacecraft design could possibly accommodate, rendering the mission impractical. This fuel constraint explains why only one NASA mission has ever successfully entered orbit around Mercury in all our decades. That spacecraft was called Messenger, launched in 2004, and it took 6.5 years to complete its journey. The reason for that extended timeline comes down to a clever technique that trades time for fuel efficiency dramatically. Instead of burning massive amounts of propellant to slow down, Messenger used the gravity of other planets as natural brakes. By flying close to Venus and Mercury multiple times, the probe let their gravitational fields gradually bend its trajectory inward. Each planetary encounter changed the spacecraft's direction and speed slightly, requiring multiple trips around the Sun to line up properly. Hence the multi-year voyage, but with fuel reserves intact when it finally arrived to stay at its destination. Following the path that Messenger pioneered, our first target won't actually be Mercury at all, but rather Venus instead. We're going to arrange our initial sunward fall so that our trajectory carries us past Venus at close range. The idea is to approach close enough that Venus's gravitational field begins exerting significant influence on our spacecraft's direction. This maneuver gets called a gravity assist because we're using the planet's gravity to help steer our ship efficiently. If gravity handles the steering, our engines don't have to work as hard, which means our precious fuel supply lasts longer. In this particular case, we'll approach Venus from an angle that allows its gravity to pull our trajectory slightly upward. We're still falling toward the Sun, but now the descent isn't quite as steep as it was immediately after leaving Earth. This adjustment lets us swing all the way around the Sun and catch up with Venus again for a second encounter. On this return pass, we'll come much closer to the planet, diving within just a few hundred kilometers of its surface. At that proximity, Venus's gravity exerts much stronger force on our spacecraft, bending our curved path even more dramatically than before. This second gravitational deflection sets us up perfectly for our first actual encounter with Mercury, though we're still not done. The Messenger mission that established this flight plan had to execute 3 separate Mercury flybys spread across nearly 2 years. Each time the spacecraft passed Mercury, the planet's gravity bent the ship's trajectory just a little bit more incrementally. With every successive encounter, our orbital path grows closer to matching the shape and speed of Mercury's own orbit around the Sun. After the third gravity assist from Mercury, we're finally positioned close enough to attempt our orbital insertion maneuver successfully. Now we fire up the main engines for the first time since we initially began our plunge toward the Sun. We time this critical burn to occur at the precise moment when we're passing closest to Mercury's surface. The small planet has relatively weak gravity, only about 1/3 the strength of what we experience on Earth's surface. But if we can reduce our velocity enough at exactly the right instant, Mercury's gravity will pull harder on our ship. That gravitational attraction becomes strong enough to overpower the Sun's influence and curve our trajectory into a stable orbit around Mercury. All of this assumes we've built a spacecraft somewhat larger and more capable than the original Messenger probe was. But we're also accepting that we'll need to perform a similar series of gravity assists to nail our final trajectory. We'll complete many loops around the Sun before we finally arrive at our destination and settle into Mercury's orbit. From the moment we left Earth's vicinity to the instant we achieve stable orbit around Mercury, the entire journey consumes roughly 5 years. That's 5 years of calculated falls, precise flybys, and patient waiting as orbital mechanics gradually work in our favor consistently. The good news is that not every planetary journey demands such elaborate choreography through multiple gravity wells and years of patient waiting. Venus, our closest planetary neighbor, offers a refreshing contrast to Mercury's brutal complexity, with a much more straightforward flight plan. From our current position, just beyond Earth's gravitational sphere of influence, we know the basic requirement: head sunward by bleeding off velocity. We fire the main engines to kill some of our orbital momentum, allowing the Sun's gravity to curve our path downward steadily. That maneuver gets us to Venus remarkably quickly compared to Mercury's torturous multi-year odyssey through repeated planetary encounters. In roughly 4 months, the Sun's gravitational pull draws us down to Venus's orbital distance, where the second planet waits patiently. But the same problem that plagued our Mercury approach resurfaces here with equal urgency, despite the shorter travel time overall. We're moving too fast for Venus's gravity to capture us into orbit without some form of intervention or additional braking. If we fail to reduce our speed significantly, we'll simply sail past Venus, just like Mariner 10 screamed past Mercury. The spacecraft will continue falling deeper into the Sun's gravity well, wasting all the time and fuel we invested already. Fortunately, Venus presents us with advantages that Mercury never could, giving us multiple tools to solve this deceleration problem effectively. For starters, Venus is substantially larger than Mercury, roughly similar to Earth in size, and therefore possessing much stronger gravity. That gravitational field has nearly 3 times more power to bend our trajectory and pull us into a stable orbit. Even more helpfully, Venus has an atmosphere, and not just any thin wisp of gas, but a crushing blanket. This atmospheric envelope is almost 100 times denser than the air we breathe on Earth's surface back home. By flying very close to the planet and deliberately skimming the upper edge of this thick atmosphere, we can harness aerodynamic drag. The atmospheric friction acts like a natural brake, scrubbing off velocity without burning a single drop of precious fuel from our tanks. We're essentially using Venus's own atmosphere as a giant speed bump to slow our spacecraft down to manageable orbital insertion velocity. Combining these two natural forces with a powerful but efficient burn from our main engine gives us everything we need. We can insert our spacecraft into a stable orbit around Venus in less than 5 months after leaving Earth's vicinity. When it comes to reaching our next destination, Mars, everything we've learned so far gets flipped on its head completely. Now we have to fly away from the Sun for the first time, instead of falling toward its gravitational embrace. That means the entire dynamic shifts from managing descents down gravity wells to climbing laboriously up them against resistance. We're trading the problem of slowing down for the challenge of building up enough speed to escape sunward gravity. Yet, paradoxically, slowing down at our destination will actually become even harder than it was at Venus or Mercury. Spacecraft from Earth have flown to Mars dozens of times over the past 4 decades, making it our most frequently visited. Through repeated missions, engineers have refined a method that prioritizes fuel efficiency over raw speed, called the Hohmann transfer orbit. The technique requires patience, because we must wait until Mars and Earth align on their closest approach around the Sun. This favorable alignment occurs only once every 2 years, creating brief windows when interplanetary travel becomes most practical and efficient. During that window, we launch from Earth and accelerate just slightly faster than our home planet's orbital velocity around Sun. That modest acceleration is sufficient to lift us gradually up and away from the Sun's gravitational well toward Mars's orbit. In theory, we could accelerate much harder and reach Mars in a fraction of the time we're planning to spend. But that approach would only create complications when we actually arrive at the red planet's neighborhood after our sprint. Because Mars orbits further from the Sun than Earth, it travels at a significantly slower speed around its track. If we're accelerating hard away from Earth right now, we'll need to shed enormous velocity by arrival time dramatically. We'd have to slow down from around 150,000 kilometers per hour to roughly 86,000. Unlike Mercury, there are no conveniently positioned planets between Earth and Mars that we can use for gravity assist maneuvers. Unlike Venus, Mars lacks a dense atmosphere capable of providing meaningful aerodynamic braking to scrub off our excess speed. Mars even has much weaker surface gravity than Earth, giving us less natural help when attempting to capture into orbit. It all comes down to using our spacecraft's engines and burning fuel to reduce our velocity enough for Martian capture. This explains why Mars missions typically take as long as 8 months to complete, despite being relatively close neighbors cosmically. We could absolutely get there faster with more aggressive acceleration, but we'd never be able to slow down enough safely. The spacecraft would blow past Mars, just like all those failed missions that arrived too hot and couldn't brake. So we take the slow road, the fuel-efficient road, matching velocities gradually so that when we finally arrive, we can stay. Our engines fire one last time to drop us into orbit, and Mars becomes our new temporary home after months. Now, Jupiter is where things start to get really interesting, because we're venturing deep into the outer solar system properly. Jupiter sits 5 times further from the Sun than Earth, meaning we're in for another extended voyage across vast distances. That separation means we can't simply hop from one planetary orbit to the next like we did for Mars's relatively nearby destination. Instead, we return to the gravity assist technique that helped us reach Mercury, but with a crucial difference in execution. On that earlier flight, we used Venus's gravity to curve our path downward toward the Sun's scorching inner regions carefully. All we need to do now is reverse our approach and use a planet's gravity to fling us outward instead of inward dramatically. Once we're on our way toward Jupiter, we face 2 distinct challenges that will test our navigation skills and patience. The first is crossing the asteroid belt, that infamous region of space between Mars and Jupiter containing hundreds of thousands. These rocky objects range from dust grains to asteroids the size of small moons, all tumbling through space unpredictably. At the velocity we're currently traveling, even a collision with a very small rock would have absolutely catastrophic results. If we were starring in a science fiction movie, this asteroid belt crossing would provide plenty of dramatic tension indeed. But in reality, space out here is mostly empty vacuum, with rocks scattered so thinly you'd be lucky to spot one. You could fly through this belt 100 times and statistically never come anywhere close to an actual collision. The asteroids spread across such vast distances that navigation through them requires no special maneuvering or defensive systems whatsoever. So after passing through without incident, we immediately encounter our second and far more serious challenge ahead. That challenge is Jupiter itself, the giant that dominates this entire region of space with overwhelming gravitational authority. This planet is absolutely enormous, containing 2.5 times more mass than all other planets combined. The gravitational force surrounding Jupiter reflects that immense mass, creating a pull almost comparable to a small star. Just like approaching the Sun earlier, Jupiter's gravity begins accelerating us inward as we draw closer to it. We transition from climbing up against the Sun's gravitational hill to falling down Jupiter's steep gravitational slope instead. That definitely helps us reach our destination faster, but it resurrects an old nemesis we thought we'd left behind. You guessed correctly. The problem of slowing down returns with a vengeance at this distant gas giant. Out here in the deep outer solar system, far from the Sun's intense gravitational grip, everything moves slowly. Remember Mercury racing around its tight orbit at 170,000 kilometers per hour near the Sun. Jupiter cruises at a leisurely 47,000 kilometers per hour by comparison, taking its time around track. Our spacecraft is traveling over 5 times that speed, meaning we've got serious work ahead to match velocities. Jupiter's powerful gravity presents both blessing and curse in equal measure for our orbital insertion maneuver here. On one hand, it pulls us in and accelerates us even faster as we approach the planet. But because that gravitational force is so incredibly powerful, it can actually bend our path into orbit successfully. Even when we're moving much faster than the planet itself, Jupiter's deep gravity well captures us effectively. We don't have to reduce our speed all the way down to match Jupiter's slow orbital progression. We only need to bleed off enough velocity to get caught in that deep well permanently. When NASA's Juno spacecraft approached Jupiter in 2016 on a path very similar to ours today here, the probe had to burn its main engine continuously for 35 minutes just to lose enough speed. So after falling sunward, speeding up, looping around Venus, getting flung outward, crossing the asteroid belt, falling into Jupiter, then slowing down again through that marathon engine burn, the entire journey from Earth to Jupiter consumes roughly 3 years. Now, here's a really interesting question worth considering carefully before we make our next move ahead. What actually happens if we don't slow down at Jupiter, but instead maintain our current high velocity? Well, the answer to that question is precisely how we unlock access to the rest of the solar system. To reach Saturn, we essentially repeat everything we just did. But this time, we use Jupiter's gravity differently. If we maintain our velocity instead of braking, we'll be moving too fast for Jupiter to pull us completely. But its gravity still has enough power to bend our path dramatically as we fly past the planet. It's like rolling down one hill, getting whipped around a sharp right turn, then immediately rolling back up. All the extra speed we gained falling toward Jupiter, we lose again as we climb away from it. The gravitational hills essentially cancel each other out mathematically, leaving us with one crucial change to our trajectory. The curve in our path now points us directly towards Saturn, our next destination in the outer reaches. Our biggest challenge from this point forward is simply the enormous distance we must cross patiently. When you look at a typical illustration of the solar system, Jupiter and Saturn appear relatively close together. But that's only an artistic convenience to fit everything onto a single page or screen for readability. In actual reality, Saturn orbits almost twice as far from the Sun as Jupiter does in space. We end up spending several years just coasting between these two gas giants with nothing to do. But eventually, after that long, quiet coast through empty space, Saturn's magnificent rings begin appearing in view. Even though Saturn is really massive, comparable to Jupiter in sheer size, it actually weighs significantly less overall. The planet contains only about 1/3 of Jupiter's mass, despite its impressive volume and ring system. That means only about 1/3 the gravitational force pulling on objects near it as a consequence. We don't have anywhere near as much resistance to push against with our engines during orbital insertion. That makes for a relatively straightforward maneuver to slow our vehicle down and become captured in Saturn's orbit. That extra coast time between the two giants extends our total journey from Earth to Saturn impressively. The complete trip from leaving Earth's vicinity to settling into orbit around Saturn takes nearly 7 years. And now the time has finally come to set our ambitious sights on Uranus far beyond. As you might expect by now, we're going to repeat our gravity-hopping procedure from inner planets. We'll use Jupiter as our big launching point to fling ourselves deep into space one more time. We can also add Saturn to that list of gravitational assists and use its pull effectively too. But there's a significant catch here that complicates our plans considerably for reaching Uranus and Neptune beyond. To use multiple planets as sequential slingshots like this, they all have to be positioned very specifically. They need to be lined up in a way that lets you swing from one to the next. Unfortunately, that favorable alignment doesn't happen often at all in human timescales or mission planning windows. The Voyager probes, launched in 1977, took advantage of a rare planetary alignment opportunity then. That perfect configuration made their grand tour of the entire outer solar system possible within reasonable time. But that opportunity won't come around again until the year 2152 arrives. Venus presents itself as our closest planetary neighbor and offers the shortest journey we'll undertake through the entire solar system. From our current position, just beyond Earth's gravitational reach, the requirements seem straightforward enough at first glance. We need to head sunward, which means firing our main engines to kill off some orbital momentum steadily. That deceleration allows the sun's gravity to curve our path downward until it intersects Venus's orbital track. The descent happens remarkably quickly compared to Mercury's torturous multi-year odyssey through repeated planetary flybys and assists. In roughly 4 months, the sun's gravitational pull draws us down to the second planet's neighborhood efficiently. But that familiar nemesis returns with equal urgency, despite our shorter overall travel time through space today. We're moving too fast for Venus's gravity to capture us without some form of additional braking intervention. If we don't find a way to reduce our speed dramatically, we'll sail right past Venus. Fortunately, Venus arms us with advantages that Mercury could never provide, giving us multiple tools for success. For starters, Venus is substantially larger than Mercury, roughly similar to Earth in overall size and mass. That means its gravitational field has nearly 3 times more power to bend our trajectory effectively. Even better, Venus possesses an atmosphere, and not just any thin wisp of gas either today. This atmospheric blanket is almost 100 times denser than the air we breathe back on Earth. By flying very close to the planet and deliberately skimming the upper edge of this thick atmosphere carefully, we can harness aerodynamic drag as a natural brake, scrubbing off velocity without burning precious fuel. It's like using Venus's own atmosphere as a giant cosmic speed bump to slow us down. We're essentially letting the planet do most of the hard work for us through pure physics. By combining these two natural forces with a powerful burn from our main engine at the right moment, we can insert our spacecraft into a stable orbit around Venus in less than 5 months total. That's 5 months from leaving Earth's vicinity to settling into orbit around our closest neighbor successfully. It's almost refreshingly simple compared to the elaborate dance we performed to reach Mercury's challenging embrace. No multiple gravity assists, no years of patient waiting, no complex choreography through repeated planetary encounters. Just a straightforward fall toward the sun, a touch of atmospheric braking, and one final engine burn. Venus proves that not every interplanetary journey demands extreme complexity or years of your life today. Sometimes the universe offers us a break, a relatively easy win to build our confidence before harder challenges. When we turn our attention toward Mars, everything we've learned so far gets completely flipped on its head. Now we have to fly away from the sun for the first time, instead of falling toward it. That means the entire dynamic shifts from managing descents down gravity wells to climbing laboriously up them. We're trading the problem of slowing down for the challenge of building up enough speed initially. Yet paradoxically, slowing down at our destination will actually become even harder than before at previous stops. Mars requires us to think differently, to work against the sun's gravity rather than with it constantly. It's a mental shift as much as a physical one, demanding new calculations and new strategies. But spacecraft from Earth have flown to Mars dozens of times over the past 4 decades successfully. We've made the red planet our most frequently visited neighbor, refining our approach with each mission. Through repeated attempts and accumulated experience, engineers have developed a method prioritizing fuel efficiency over raw speed entirely. It's called the Hohmann transfer orbit, named after the German engineer who first calculated these trajectories mathematically. The technique requires patience because we must wait until Mars and Earth align on their closest approach. This favorable alignment occurs only once every 2 years, creating brief windows when interplanetary travel becomes practical. During that window, we launch from Earth and accelerate just slightly faster than our home planet's speed. That modest acceleration is sufficient to lift us gradually up and away from the sun's well. In theory, we could accelerate much harder and reach Mars in a fraction of the time. But that approach would only create massive complications when we actually arrive at the destination finally. Because Mars orbits further from the Sun than Earth, it travels at a significantly slower orbital speed. If we're accelerating hard away from Earth right now, we'll need to shed enormous velocity by arrival. We'd have to slow down from around 150,000 kilometers per hour to 86,000. Unlike Mercury, there are no conveniently positioned planets between Earth and Mars for gravity assist maneuvers. Unlike Venus, Mars lacks a dense atmosphere capable of providing meaningful aerodynamic braking to help us slow. Mars even has much weaker surface gravity than Earth, giving us less natural help during capture attempts. It all comes down to using our spacecraft's engines and burning fuel to reduce velocity sufficiently. This explains why Mars missions typically take as long as 8 months to complete the journey. We could absolutely get there faster with more aggressive acceleration, but we'd never slow down enough. The spacecraft would blow past Mars, just like all those failed missions that arrived too hot. So we take the slow road, the fuel-efficient road, matching velocities gradually over many months, patiently. Our engines fire one last time to drop us into orbit, and Mars becomes ours after 8 months. The red planet awaits, with its rusty surface, its frozen polar caps, its ancient dry riverbeds. We've conquered another world, added another destination to our growing list of planetary victories achieved successfully. But as impressive as Mars feels, it's still part of the inner solar system's familiar territory. Everything changes when we set our sights on Jupiter, where things start getting genuinely interesting for us. Jupiter sits 5 times further from the Sun than Earth, meaning we're in for an extended voyage. That separation means we can't simply hop from one planetary orbit to the next any more easily. Instead, we return to the gravity assist technique that helped us reach Mercury previously, but flipped. On that earlier flight, we used Venus's gravity to curve our path downward toward the Sun. All we need to do now is reverse our approach and use a planet's gravity to fling us. Once we're on our way toward Jupiter, we face 2 distinct challenges that will test us thoroughly. The first is crossing the asteroid belt, that region of space between Mars and Jupiter teeming. These rocky objects range from dust grains to asteroids the size of small moons tumbling. At our current velocity, even a collision with a very small rock would have catastrophic results. If we were in a science fiction movie, this crossing would provide plenty of dramatic tension. But in reality, space out here is mostly empty vacuum, with rocks scattered incredibly thinly. You could fly through this belt 100 times, and statistically, never come close to collision. The asteroids spread across such vast distances that navigation through them requires no special maneuvering. So after passing through without incident, we immediately encounter our second and far more serious challenge. That challenge is Jupiter itself, the giant that dominates this entire region of space with overwhelming authority. This planet is absolutely enormous, containing 2.5 times more mass than all others combined. The gravitational force surrounding Jupiter reflects that immense mass, creating a pull almost comparable to stars. Just like approaching the Sun earlier, Jupiter's gravity begins accelerating us inward as we draw closer. We transition from climbing up against the Sun's gravitational hill to falling down Jupiter's steep slope. That definitely helps us reach our destination faster, but it resurrects an old nemesis we encountered. You guessed correctly. The problem of slowing down returns with a vengeance at this distant giant. Out here in the deep outer solar system, far from the Sun's intense grip, everything moves. Remember Mercury racing around its tight orbit at 170,000 kilometers per hour near Jupiter, cruises at a leisurely 47,000 kilometers per hour by comparison, taking its sweet time. Our spacecraft is traveling over 5 times that speed, meaning we've got serious work ahead today. Jupiter's powerful gravity presents both blessing and curse in equal measure for our orbital insertion maneuver. On one hand, it pulls us in and accelerates us even faster as we approach. But because that gravitational force is so incredibly powerful, it can bend our path into orbit. Even when we're moving much faster than the planet itself, Jupiter's deep well captures us. We don't have to reduce our speed all the way down to match Jupiter's slow progression. We only need to bleed off enough velocity to get caught in that deep well permanently. When NASA's Juno spacecraft approached Jupiter in 2016 on a path similar to ours today, the probe had to burn its main engine continuously for 35 minutes just to lose. So after everything, falling sunward, speeding up, looping around Venus, getting flung outward, crossing the asteroid belt, then falling into Jupiter and slowing down again through that marathon engine burn, we've finally arrived. The entire journey from Earth to Jupiter consumes roughly 3 years of our lives in total. 3 years of calculations, course corrections, patient waiting, and trusting the mathematics of orbital mechanics completely. But now we face a really interesting question worth considering carefully before making our next move. What actually happens if we don't slow down at Jupiter, but instead maintain our current velocity? The answer to that question is precisely how we unlock access to the rest of the solar system beyond Jupiter's orbit permanently, opening doors to worlds most humans will never see with their own eyes during their lifetimes on Earth. The distant frozen giants waiting patiently in the outer darkness, where sunlight barely registers anymore as anything more than another bright star among countless others in the endless black void of deep space, where things get really interesting. To reach Saturn, we essentially run the same playbook we just executed at Jupiter, but with one critical adjustment to our strategy. This time we use Jupiter's gravity not as a brake to capture us, but as a slingshot to fling us even deeper outward. If we maintain our current velocity instead of slowing down, we'll be moving too fast for Jupiter's gravity to fully capture our spacecraft. But that immense gravitational field still has enough power to bend our path dramatically as we scream past the giant planet's cloud tops. It's like rolling down one steep hill at full speed, getting whipped around a tight hairpin turn, then immediately climbing back up another. All the extra velocity we gained falling toward Jupiter, we lose again as we climb away from it on the other side. The gravitational hills essentially cancel each other out mathematically, leaving us with one crucial gift: a completely new trajectory pointing us precisely where we want. The curve in our path now aims us directly towards Saturn, our next destination waiting patiently in the outer solar system's darkness. Our biggest challenge from this point forward is simply the sheer distance we must cross between these two gas giant neighbors. When you glance at a typical illustration of the solar system in a textbook or poster, Jupiter and Saturn appear deceptively close together. But that's purely an artistic convenience to fit everything onto a single page or screen without making the image impossibly wide. In actual reality out here in the black, Saturn orbits almost twice as far from the Sun as Jupiter does in space. We end up spending several years just coasting silently between these two giants, with absolutely nothing to do but wait patiently and hope. But eventually, after that long, quiet drift through the emptiness, Saturn's magnificent rings begin appearing in our forward view, growing larger slowly. Even though Saturn is genuinely massive in size, comparable to Jupiter in sheer volume and presence, it actually weighs significantly less overall. The planet contains only about 1/3 of Jupiter's mass, despite its impressive girth and those spectacular rings encircling its equator. That means only about 1/3 the gravitational force pulling on objects near it, as a natural mathematical consequence of less mass. We don't have anywhere near as much resistance to push against with our engines during the orbital insertion maneuver we'll perform soon. That makes for a relatively straightforward procedure to slow our vehicle down and become permanently captured in Saturn's gravitational embrace at last. The extra coast time between the two giants extends our total journey from Earth to Saturn out to nearly 7 full years. 7 years of our lives spent traveling, waiting, calculating, trusting the mathematics of orbital mechanics to deliver us safely to this ringed wonder. 7 years watching Earth become just another star in the black, indistinguishable from countless others, unless you know exactly where to look. And now the time has finally come to set our ambitious sights on Uranus, that distant ice giant lurking far beyond Saturn. As you might expect by now, after completing so many planetary encounters, we're going to repeat our gravity hopping procedure once more. We'll use Jupiter as our primary launching point to fling ourselves deep into space with enough velocity to reach the outer limits. We can also add Saturn to that list of gravitational assists and use its pull to curve our path one final time. But there's a significant catch here that complicates our plans considerably for reaching both Uranus and Neptune beyond it in reasonable time. To use multiple planets as sequential slingshots like this efficiently, they all have to be positioned very specifically when you first launch. They need to be lined up in a way that lets you swing from one to the next without wasting years waiting. Unfortunately, that favorable alignment doesn't happen often at all in human timescales, or even across multiple generations of mission planners and engineers. The Voyager probes, launched back in 1977, took brilliant advantage of a rare planetary alignment that occurs only every few centuries. That perfect configuration made their legendary grand tour of the entire outer solar system possible within a single, reasonable mission time frame successfully. But that opportunity won't come around again until the year 2152 finally arrives, more than a century ahead. And by that time, assuming humanity hasn't destroyed itself or abandoned space exploration entirely, we'll probably have developed warp drive technology anyway. When that day comes, we'll be able to travel anywhere in the solar system almost instantly, making all these careful calculations irrelevant. But there's still hope for reaching Uranus in our lifetimes without waiting for magical technology that doesn't exist yet right now. There is a launch window opening in the year 2031 that would allow a spacecraft to use gravity assists cleverly. Venus and Earth can both be leveraged to launch a probe out on a path to intersect Uranus in about 13 years. That's not too terrible, considering that it took the Voyager 2 probe about 9 years to get there using the special alignment. 9 years versus 13 years feels like a reasonable trade-off, given that we're working without the perfect planetary configuration that made Voyager's journey. So we're looking at 13 years of travel time to reach Uranus, assuming we launch during that specific window and everything goes. 13 years of coasting through the outer darkness, where the sun looks like just another bright star in the endless black void. 13 years watching the ice giant grow slowly larger in our forward view, until its pale blue disk finally dominates our entire field. 13 years of wondering what we'll find when we finally arrive at a world so distant that sunlight barely warms it. Neptune represents the furthest planet from the Sun in our solar system, at least according to the official definition that demoted Pluto. The distance we're looking at now is genuinely unfathomable to the human mind, stretching beyond what our earth-bound brains can truly comprehend. It's 30 times further away from the Sun than Earth is, a distance so vast that light takes 4 hours to cross. It's 6 times further than Jupiter, that giant we spent 3 years reaching and thought was impossibly distant at the time. Out here at Neptune's orbit, light from the Sun barely even registers as warmth, just another point of light in the sky. After using a gravity assist from Uranus to curve our path one final time, it took the Voyager probe another 3 years. About 12 years in total flight time from Earth to Neptune. 12 years of traveling through the outer solar system's frozen wasteland. But those probes didn't have powerful engines on board, capable of sustained burns or course corrections beyond minor trajectory adjustments carefully planned. They relied entirely on gravity to steer them out this deep into space, using planetary encounters as their only means of navigation. Over such a long distance, spanning decades of travel time, our spacecraft could probably start catching up even without a perfect alignment. Our more powerful engines give us flexibility that Voyager never had, allowing us to make course corrections and accelerate when needed strategically. That makes our realistic travel time more like 15 years at the most to reach Neptune from Earth and settle into orbit. 15 years of our lives invested in reaching the last true planet in our solar system's outer frontier, where few will. 15 years of patient waiting, trusting the calculations, hoping the hardware holds up under the stress of deep space travel conditions. 15 years watching Neptune grow from a faint blue dot to a world, a destination, a place we can finally call conquered. Now, technically, Pluto is not a planet anymore, according to the official astronomical definition adopted in 2006, controversially among scientists. But let's go there anyways, because it's genuinely cool, and because there actually has been one successful NASA mission to Pluto. That mission was a probe called New Horizons, launched in 2006 on a trajectory optimized for speed over everything else. The only problem was that by the time it got all the way out here to the very edge of the solar system, it had nowhere near enough fuel remaining to slow down and get caught in the orbit of such a small object. You see, Pluto travels around the Sun at about just 17,000 kilometers per hour due to its distant, lazy orbit out here. Meanwhile, New Horizons was traveling at about 83,000 kilometers per hour by the time it reached Pluto's orbital distance, finally. That's nearly 5 times faster than the dwarf planet itself moves, making orbital capture essentially impossible without massive fuel reserves for braking. By using this high-speed strategy, the probe was able to fly from Earth to Pluto in just about 10 years total. 10 years to cross the entire breadth of the solar system and reach the icy frontier where sunlight is a distant memory. But if we wanted to continue our streak of arriving and orbiting every planet and non-planet out here in the system successfully, then it would be closer to 20 years before we actually arrive at Pluto to stay permanently in its gravitational embrace. 20 years of travel time to reach a world so small and distant that many scientists don't even consider it worthy. 20 years watching the sun shrink to just another star, unable to distinguish it from the background without precise instruments and calculations. 20 years of wondering what drives us to explore these frozen wastelands so far from the warmth and light we evolved under. 20 years of proving that humans can reach anywhere in our solar system given enough time, patience, and stubborn determination to succeed. So we've just completed a grand tour, visiting 8 planets, plus one controversial dwarf planet at the solar system's frozen edge. How long does that all take when you add up every individual journey, every gravity assist, every patient coast through emptiness? Well, if you sum it all up carefully, we've clocked just over 64 years traveling to each destination in the solar system. 64 years of your life invested in becoming the first human to orbit every major world circling our sun successfully. That's probably the kind of endeavor that you'd want to start young, maybe launching on your 20th birthday and arriving at Pluto. Or you could choose your favorite destinations strategically, picking just a few worlds that call to you most strongly emotionally and culturally. Maybe you only care about the rocky inner planets, where humans might someday build colonies and terraform alien landscapes into new. Maybe you're drawn to the majestic gas giants, with their storms larger than Earth, and moons that could harbor hidden oceans. Maybe you're willing to sacrifice everything for the frozen outer frontier, where few will ever venture during humanity's entire existence here. The choice is yours to make, but the clock is always ticking, and these journeys demand decades of your finite lifespan. But if you want to start learning about every planet in exquisite detail right now, without leaving Earth's comfortable surface behind, then there's no better place to begin than Mercury, that scorched world orbiting closest to the sun's furious heat and light. Discover the shocking discoveries NASA found there, the mysteries hidden on a world that seems too hostile for anything interesting whatsoever, surprisingly. Learn how Mercury's iron core makes up 85% of the planet's radius, far more than any other world proportionally. Explore the evidence of ice hiding in permanently shadowed craters at the poles, despite surface temperatures reaching 430 degrees Celsius. Understand why Mercury's day lasts longer than its year, creating bizarre sunset patterns that would confuse any Earth-based biological clock completely. The solar system awaits your exploration, whether you travel there in person or through the vast knowledge we've gathered over decades. Every world tells its own story, holds its own secrets, offers its own unique contribution to understanding our cosmic neighborhood's history.